Hello all, we use linear dropout regulators in our circuits, right? So, linear dropout regulator belongs to the family of linear regulator, right? So, linear regulator, when compared to switching regulator, has a high power dissipation, which is the major disadvantage, but it has low noise. That's the advantage, right? So, for the linear regulator or the LDO, calculating the power dissipation and then how much junction temperature of the LDO is rising is very important. So LDO you might get saved because the difference between the input and output voltage is less, but sometimes we use LDO for good amount of voltage difference between input and output, right? In this video, we will see how to calculate the junction temperature rise of LDO. So, why should we calculate the junction temperature rise, first of all? So, the first thing that we have to remember is whenever we use this LDO at a particular ambient temperature is the temperature around the electronics, right? The surrounding temperature, right? So let us assume we are using this particular a particular board with ambient temperature of 50 degrees. So that means the outside temperature is 50 degrees. Okay, and when we use this, and if we use this particular LDO to give a current of 50 milliamps. Okay, let us assume 50 milliamps is the load. In that case, the amount of power that is dissipated in the LDO and due to which how much the junction temperature of this LDO rises is to be calculated. Okay, so and this is very important because this particular junction temperature rise should not exceed the maximum junction temperature specification of the LDO. So for this we have taken TPS 76201 LDO, for which we are considering input voltage of 5 volts, output voltage of 3.3, and as we said the current is 50 milliamps, and the other specifications will derive from the data sheet. Okay, so this, if you see here, the maximum power dissipation. Okay, so the maximum power dissipation value can be seen from the data sheet. So this is a TPS 76201. As we are considering the power rating, so if you see here, the maximum power dissipation, again it is depending on the package. Okay, let us assume we have a particular package and this is the maximum power dissipation, 305 milliwatt. It is at 70. Let us consider the same at 50, 305 milliwatt. Okay, so that means 0.305 watt, right? That is the maximum power dissipation. And then maximum junction temperature. So the maximum junction temperature can be seen in this particular data sheet. Okay, if you see here, the maximum junction temperature is around 150 degrees. Okay, so we can consider 150 as the maximum junction temperature. So these are the inputs that are required to calculate the power dissipation and then the junction temperature. So the first thing, power dissipation. Power dissipation is nothing but the amount of power that is dissipated in the LDO, which is directly given by, okay, V in minus V out. V in is 5 volts, right, minus V out. Okay, and then into the amount of output current that is flowing through. Okay, 0.05, which is the 50 milliamps load that we have considered. So that means the amount of power dissipation is 85 milliwatt. Okay, so this is the power that will be dissipated. Now, if the ambient is 50, okay, what would be the temperature rise with this power dissipation? That can be calculated by ambient plus. Why we should do ambient plus is already there is a temperature of 50 around the electronics, right, on the electronics board on which this LDO is mounted. So that means any temperature that any power that is dissipated in the LDO will be above the ambient temperature. So that means it will be 50 plus, and power, this is the power that is dissipated into, okay, and then the ambient junction, the maximum junction temperature minus, okay, and then 25. So that means 150 minus 25 divided by maximum power dissipation. Okay, this is the formula. Okay, so what we are doing is the maximum junction temperature rise minus, okay, this will not be 25. What we will be considering is okay, 20, because that is the generic ambient temperature, right? We can consider 25 divided by the maximum power dissipation. Okay, so which is very clear, into the power dissipation. Okay, and then if we enter this, you can see the junction temperature, okay, for an ambient of 50 degrees with this power dissipation has gone to 84 degrees centigrade, which is well beyond 150. Okay, and this is in watt. Okay, this is in degrees centigrade. Okay, so this is how we calculate. So the formula is very clear, right? Ambient, you can see here, ambient plus the power rise, which is G4, the power dissipation, into the amount of temperature rise, right? G11 is maximum minus 25 divided by 0.305. This is how we calculate the junction temperature. So as we see here, the specs that are required are these are the specs. We need the load current, we need the input voltage, we need the output voltage, we need the maximum power dissipation from the data sheet of the LDO, and then we need the ambient temperatures. That means the surrounding temperature at which we are going to use this. So example, if you're talking about a industrial domain product, and you have a maximum of 85, so this will change to 85. So once you have this formula, right, you can change the temperature, okay, and then you can, okay, so here what we'll do is, instead of 50, if we change this to this value, okay, so as and when if you change this, you can see, you can check the junction temperature rise. Okay, so let us assume you are using at 125. Okay, so that means this particular LDO, if used at a temperature of 125, will exceed the junction temperature of a spec of this LDO. So that means this particular LDO might not be suitable if you want to use this for a automotive grade product. So this is how you can calculate and decide on whether to use LDO in a specific application or not. So two things we are calculating here. One is power dissipation and the second one is the junction temperature.